Hello, this is Practical Tasks 8.1. This is a task that is broken into basically parts A to E, and each part has your understanding or my understanding of graph traversal, connectivity, shortest paths, and algorithm complexity. This is touching graph representation, traverse algorithms like BFS, DFS, connectivity testing, can't say this name, Dijkstra's algorithm, theoretical analysis of algorithm changes. For part A, we have the scenario of Miss Maple, um, where the task is basically trying to find the most accessible hotel in this given scenario here that I'm not going to read, otherwise it's going to become a 1 hour video. Miss Maple's problem can be solved efficiently using the BFS. Because the graph is unweighted, all ages have a unit weight of 1. BFS naturally finds the shortest path from the source nodes to all other nodes in the graph. To determine the number of shortest paths to each hotel, we maintain distance array. We get a distance there. Path count array. We get the counting. Top one stores the shortest distance from the train station to every other node. And this path stores the number of shortest path from S to each node. This is the algorithm explanation. So you create a disk array where this zero source and initialize all other distance to infinitum. Create an count array where counts is one way to be at the start, and initialize others to 0. Use a queue for blah blah, BFSS traversal. BFS traversals, you process each node in the queue, and then for each adjacent node V, update distance V, and account V. It can become very complex if I try to explain in that way, but in a nutshell, the algorithm you initialize this way, and then you process the BFSS traversal, and then from that you extract the hotel's data. This is the pseudocode function for the file for find shortest path. Has these two parameters: initialize, done, and as that. And then you returns the number of shortest paths to all nodes. So initializes BFS Q, first time visiting F, inherit path from U, another shortest path to V, till the result. Complex analysis, the time complexity for that is big O n plus m, where each node is used once and each age is processed once. That's why the n plus m. So the overall time then is the combination of these two, which satisfies the given constraint. It's not the question. Bit of a proof of correctness, if you're interested. Then part B is about network connectivity. To check if the network graph GGG is connected, we perform a breadth first search, BFS and DFS, starting from any node and count the number of reachable nodes. If all nodes are reachable, the graph is connected, otherwise it's not. The algorithm that it follows these steps. This is the pseudocode. For the function is connected. uh, with empty graph, and from that expose the neighbors. And if true, true if all nodes are visited, and it returns why it works. It works because of these reasons here. Part C, DFS on a adjacency matrix. The running time complexity of DFSS with the adjacency matrix. When using adjacency matrix representation, it checks if an edge exists between two nodes, takes that time, iterates over all neighbors of a node, takes big O n time, since we check an entire row of the matrix, like in a line. And then the complex analysis of this combined will end up producing this. So if you compare this to this, you can see that they can be used for different ways, different purposes in different contexts. Then part D is this funny hard name to say algorithm on a cost matrix. Step 1, you construct your graph. Step 2, you run the algorithm starting at node 1, initialize, and then you execute it that way. Here's a step-by-step execution. And here's the order of nodes removed from the priority queue. Shortest path tree. As you can see here. Looks beautiful. And then lastly, part E, edge weight shift impact. No, PP may not necessarily mean the shortest path from SS to TT if each edge weight is increased by 1. Explanation. Let the original shortest path PP have edges E1, E2, etc. until EK with total weight. The big After increase all edge weights by 1, what do? That's the result. For an alternative path Q with M edges in original weight, the new weight becomes that. All this to reach this. Since the increase is proportional to the number of edges, a previously known shortest path with fewer edges might now become the shortest due to a smaller total increase in weight. In conclusion, increasing all edge weights by 1 can change the shortest path because it alters the relative cost between paths of different lengths. In a nutshell, part A, count multiple shortest paths from a source using BFS. Part B, check the network connectivity using DFS and BFS. Part C, analyze DFS complexity with different graph representation. Part D, solve DTRIS manually from an adjacency matrix. And part E, understand how uniform weight increase affects shortest path. And that's it for task 8.1. Thank you.